I don't know. I don't know if any of y'all are around, and if you can see the live stream or not. I got it going here. If not, we're gonna be in a little bit of a problem. Where's my channel? Should be showing a live stream. Okay, now it says live now. Okay. So the live stream is up. I'm just gonna put it right in the channel if you need it. And once I confirm that it's working, yeah, there we go. Okay. So let's get back into the exam review. Sorry about that, guys. Like I said, we're recording this, and this is going to be a much shorter, easier video to get online than our other longer, all-day long recordings. So if you have to jump out of this, don't worry about it. You'll be getting an email from me probably this evening with how to close out the class. But the point is, when you take out a loan on a solar array, the interest on the solar array will basically double its cost. And so if you have a 30-year loan, the payback of the solar array has to be less than 15 years in order for that loan not to cost more than the electric payments the customer would already be making. And so when you have to be very careful when you combine loans with solar. If you have a 15-year payback, you need a 30-year loan. If you have a 5-year payback, you need a 10-year loan if the goal is to have the loan payments be less than what the cost to have if you want the solar array to pay off the loan, then the payback of the system has to be half of what the loan term is. Otherwise, the interest rates kill you. So it's what this question, this really bad, I think this is the worst question, but what this really bad question is saying is that the interest rates on the loans are overlooked. And the thing is, you might say, well, that's an awful question. You're not going to have these exact same questions on the exam, and so they might approach similar subject matter differently. The point is the financing on solar is underappreciated. Okay, I'm surprised so many did so well on this one because we didn't really cover it in class, and there's something that I'm really proud of y'all in particular for getting right on this. So it says a renewable energy credit is a tradable unit of electricity generated by a renewable resource. Whatever that means, we didn't really cover it. We have a commercial battery class where at the very end we talk about green energy transactions, and New Jersey is actually a leader in the renewable energy credit market. So we did just briefly talk about how there's a carbon credit that you get in New Jersey for these things that are worth more than the cost of electricity itself. And that's a renewable energy credit. Now, as to the answer, the clue is energy. The clue is that it's asking for an energy unit. So power is wattage. So we got 1 megawatt, we got 1,000 megawatts. That wattage is instantaneous. Energy is wattage multiplied by time. And so energy is measured in watt hours. And so these wattage based answers are not correct, and everyone in class picked an energy unit. Everyone either chose a kilowatt hour or 1,000 kilowatt hours, and that's great because a kilowatt hour is a unit of energy. You take out the H, you don't have kilowatt hours anymore, you have kilowatts, That's instantaneous. That's power. That's instantaneous. Wattage is instantaneous. Energy is wattage multiplied by time. So the correct answer is 1,000 kilowatt hours. If one of these certificates was issued for every single kilowatt hour in existence, there'd just be 1,000 times more of these certificates to manage. So this is arbitrary, but a renewable energy certificate is equal to 1,000 kilowatt hours of electricity. So if you think memorizing something like that is hard now, imagine memorizing that a week ago when you didn't know anything about solar. This is now, at least we're talking kilowatt hours. A renewable energy certificate or renewable energy credit is 1,000 kilowatt hours. Which of the following is a common financing product for the purchase of a residential energy system? This is also a hard question in its ambiguity. I mean, the NABCEP PV installer exam is not necessarily harder. There's more math on the PV installer exam. There's more code on the PV installer exam. But at least with math questions, at least with code questions, they're more clear than these ambiguous ones. So we really have to sit back and say, I don't know a lot of these terms. What on earth is the right answer going to be? So it says, what's a common financing product for purchasing a residential system? And most of y'all got, I think, what a very good answer would be, which is net metering. If you don't have net metering, and we talked about net metering a lot in class, net metering has to do with the buyback rate from the utility. And so what the utility is paying for the electricity, everything in the world has to do with that. All of solar has to do with what the utility is willing to pay for the electricity. And so the net metering policy for residential is very important. They're asking what is a financing product for purchasing residential system, and they're referring to a lease. They're calling a lease or a loan or a direct cash buy is how people pay for solar. And they're even saying, if you get financing, if you go get your car financed, you might get a car loan or you might get a car lease. And both a loan and a lease are financing products. So the right answer is a solar lease. It's not the estimate. It's not the guarantee. In fact, these are too close together of answers for them to be correct. It really is a choice between net metering and solar leasing. And net metering is a policy, and it's an important policy. It's such an important policy that I think you could argue it's a financial product and that it's a common one. So I don't think everyone who said net metering, I think you gave a good answer, but the correct answer in this case is a solar lease. They're making a more direct question on saying which of these terms is a financing product, and a solar lease is a loan. Basically, there's different rules for loans versus leases, but basically a solar lease is a financing product. For which of the following systems should a system owner expect for maintenance cost over the life of the system? We didn't really talk about this one. Solar panels are 25-year products. They have a performance warranty for 25 years. The actual warranty, the what we would consider to be a warranty, is commonly 10 years, but for whatever reason, the solar industry says, there's two warranties on a panel. It's build quality and how long it'll produce electricity if it were in a perfect environment. and how long it would produce electricity in a perfect environment, that warranty is a 25-year warranty. Inverters are expected to fail once or twice during the life of the system. So the inverter is the heart of the system. It's the muscle of the system. It's pumping the electrons from the solar array into your AC home electronics. So the inverter is where a lot of the cost is. The inverter does a lot of the work. The inverter, if something fails, not because of the installer, but because the system is just being used day in and day out, it's the inverter that's going to fail. So the inverter is the right answer to this one. So it's a weird question again, but it's out of the system warranties, you're generally paying for those at upfront. Module replacement, you're paying at the end of the life. After the system's life is over, you might replace the modules. The inverter is something you're going to replace once or twice over the life of the system. Again, not a great question. Microinverters are warranted for 25 years along with the solar panel, but most other inverters are warranted for maybe 10 years, 15 years, sometimes 5 years. Hey, this is a really good job because most everyone got the answer right, and this is one of the only questions that involves some math. It says, what is the maximum number of solar panels allowed in a string with these certain specifications? The reason why we got to get all the ambiguous questions correct is you might miss the math questions. I like to kind of guess at the math questions first, and then maybe at the end go back and see if I can't figure them out a little bit better. But what we have here is a maximum system voltage of 600 volts. And then we have the record cold temperature being minus 10. And then we have a temperature coefficient of voltage given where it's a negative percentage, about 0.3, per degree Celsius. So we got a degree Celsius here, we got a negative percentage here at a cold temperature, and then we have its normal maximum voltage, and then this other one here, this VMP, is more of its operating voltage. So often with these solar electronics, we'll get a voltage. The OC stands for open circuit. And then you got this other one, it stands for maximum power point tracker, but this lesser voltage right here is really its operating voltage versus its maximum voltage. So we have the maximum voltage, we have an operating voltage, we have a temperature coefficient, and we have a record low temperature, and then we have a clearly defined maximum system voltage. So what we do with this is twofold. The first is we need to figure out the temperature impact on voltage. And if you don't know that a solar panel is done at a standard test of 25 degrees Celsius, if you don't know that on this question, then you're almost dead in the water because of because the standard solar panel, what your voltage is given at, what your amperage is given at, what this temperature coefficient adjusts around, is that solar panels are tested in a laboratory environment, and that lab condition is 25 degrees Celsius. So the way the math works, I don't think we ever actually went through and calculated this. But the way the math works is we have a 35 degree difference between -10 and 25. And so we have a 30 Let's off my calculator. We got let me clear this stuff out. Be a little bit neater. We got a 35-degree Celsius difference between the coldest temperature on record of -10 and what wasn't shown, which is that the standard test condition is done at 25 C. And so we have a 35-degree difference, and we have a negative 0.3% per degree Celsius. And so, 0.3% of 35 is about 10. And it's going to be a negative 10%. And so it's the voltage is for cold temperatures, the voltage is going to increase by about 10%. Is basically how that goes. As the temperature increases by 35 degrees, the voltage will decrease by 10%. As the temperature decreases by 35 degrees, the voltage will increase by 10%. And so we got a 25-degree test rating. We've decreased the temperature by 35 degrees, and so the voltage is going to increase by 10%. And so that brings that 81 maximum volts. And we always design around this open circuit maximum voltage. We never design around the operating voltage or amperage. If you design around what the open circuit voltage will be, if the system is just magically hovering at 81 volts when it's not operating, if we design around that 81 volts being the maximum, then any adjustments we make are made to that maximum, and we're always going to be in a safe, margin of error. So, I guess what we can say is this is done at 81 volts, and if it increases by 10%, 81 volts plus another 8 volts is going to be 89 volts. That's at -10 degrees. And let's see here. It should be 600 volts divided by 89 is giving you 6 and change, and you can't have 3/4 of a solar panel, and so the correct answer is 6 panels. It's like, okay, well, you had to know a lot to get this answer correct. You had to know the 25-degree difference, actually the 35-degree difference, and then you had to take that degree difference and use the temperature correction factor, and then you had to use that temperature correction factor to say, okay, this is, as the temperature increases, the voltage decreases. So now as the temperature decreases, the voltage increases because of this negative sign. So now we had to say, okay, now the voltage, we're at a colder temperature, so the voltage is increasing, and instead of being at 81 volts per module, we're at 10% higher than that. And then we had to divide the 600 volts by that. So that was a lot of math that we had to do. I imagine some of y'all used my kind of standard, if you don't know what the answer is, oversized by 25%, to kind of get you to this answer. So I don't know how many of y'all went all the way through the math, but you made a good guess nonetheless. If I were doing kind of some guesswork on this, I could say, okay, well, six solar panels times 81 volts is going to give me 4 86 volts times 1.25 is right around 600. So maybe that's how y'all got there or not. I don't really know. I guess for now, for the purpose of educating ourselves, this homes cannot have more than 600 volts in them. Businesses can be 1,000 volts. Sometimes utility scale plants are even higher than that. But for homes, the 600 volt limit cannot be exceeded under any circumstance. And so that is generally calculated by taking the normal maximum system voltage that the array is going to be producing and then adjusting that for the coldest temperature of the year and making sure at the coldest temperature of the year the system does not exceed 600 volts. So that's where it's coming from. Not much you can do about that other than be lucky or do the actual calculation. Which is the best tool to verify the open circuit voltage of a PV module? The answer is a multimeter. I call this thing a voltmeter, but a multimeter does volts and amps, so it's not just a voltmeter, it's a multimeter. Okay, ammeter will just do amperage. A megameter does ground rod resistance testing. An oscilloscope does, you model the sine wave of AC electricity, which you can use oscilloscope testing to test power quality. But the electrician's multimeter is the answer here. All right, next question. Which process is used to increase the conductivity of semiconductors? So we really did not spend time on this. I think in one of the cartoons that Susan posted, it covers this more, but it's called a process called doping. Again, this is just you might not pick up on this stuff first time through knowing nothing about solar. They haven't come up with enough questions to test some kind of solar knowledge, and this test is really skewed more towards the design end of things than the install end of things, and it's for both designers, project managers, and installers. So sometimes the best way to prepare for these exams is to come back here and do this practice exam over again right before you go and take the real thing, so that some of these terms that are going to leave your head as soon as you're done with class are at least there for that moment. Like when I'm taking my electrician's exam, I'm taking 2 practice exams the day before, and that's the best thing I can do to study. So coming back and reviewing this exam the day before is the best thing you can do to study for it. You can also just stay up with solar training videos, maybe watch some of the other videos in other portions of this classroom to pick up on more stuff. But hey, what doping is they take what's a good way to describe doping? What I like to describe it as is imagine a billiards table or a pool table where you pick up half the table and all the balls roll down to the other side of the table. So what they're doing with doping is they're taking a piece of silicon and they're making the top of the silicon be different than the bottom of the silicon. And so when these electrons get energized, the difference between the top of the silicon and the bottom of the silicon causes the electrons to stack up on one side of the silicon. So they take silicon and they coat the top and the bottom in different chemicals, and just the difference in the chemicals is enough to get those electrons to move to one side and not the other. So doping is the correct answer on for this question. The sun passes over how many degrees of longitude each hour as it tracks across the sky? And I admit I got this question wrong, but I shouldn't have. I said 24 when I did this practice exam, and I was thinking latitude, not longitude. Now, what's the difference? So here's the Earth, and like the polar ice cap is at a high latitude. You know, the equator is at a 0 degree line of latitude, and the southern ice cap is at a low latitude. Now, okay, that's fine. The top of the United States, there was there's this like let's go take over Canada kind of slogan that was like all about the 48th parallel. And so back when the United States was trying to take over this new world, everyone said, let's get our country up to the 48th parallel or bust. That's kind of up around like Seattle, Maine, Montana is up in the 48th parallel. Texas is right down around the 30 degree line of latitude, and the tropics of Cancer and Capricorn, I think, are even lower than that. So these are all lines of latitude. This question is not asking about latitude. This says longitude. So each hour as the sun goes across the sky. Well, as the sun goes across the sky here, from east to west and back around, that's making a circle. A circle's 360 degrees. And so if we take, 360 degrees, the sun moving, it's really the Earth moving around the sun, but we'll just say it's the sun moving around the Earth. One way or another, one of them is making a circle around the other, and it's happening in a 24-hour period. And so if we're talking about, the Earth, and we got our lines of longitude, and it's, how fast does the sun move across those lines of longitude? And we got 360 degrees done over a 24-hour period. So we have 360 degrees done over a 24-hour period. That's a 15 degree. It's 15 degrees per hour. And so the correct answer is 15 degrees per hour. There's another common question if they're not answering about longitude. So, longitude, it's common to be 15 degrees per hour. And if longitude, if you remember, longitude are the lines that are always long. It says longitude, they're always long. The North Pole and the South Pole, those are little bitty circles, and the equators are real big circles. So those latitude, the circles are small at the tops of the Earth and big around the middle. Longitude is always going to be this long line, that circles the Earth from north to south. So if you can just remember that longitude, it's 360 degrees divided by 24 hours. In the test software, there's a calculator. So you're going to have to do a bunch of clicking, but there's a calculator that you can click on. The other question is, how much does the sun move across the sky in terms of lines of latitude? And that one, the you have to know a little bit about geography, and I have to always go refresh my head about this whenever I'm studying for a solar exam. But there's these. There we go. That's a good one right here. Yeah. So here we have a map, and on top of this map we got the equator, then we got the Tropic of Cancer, and we got the Tropic of Capricorn. And the reason why these are interesting is because the sun is like directly overhead at the equator. It's like straight up, okay? And as the sun moves in for winter or summer, it's moving along this Tropic of Cancer and Tropic of Capricorn, and then back down to the equator. So the sun's moving like 24 degrees from its lowest part in the sky to its highest part in the sky. It's like a 24-degree seasonal shift. And so going back into our exam, this 24-degree answer is often the right answer if it's talking about latitude. There's a common question about how much does the sun move in terms of latitude between summer and winter, and the answer is 24 degrees. It's that difference between the equator and the Tropic of Cancer, or the equator and the Tropic of Capricorn. So this is almost like a guaranteed free point on the NAPCEP exam. If longitude, if you know that it's going to be associated with 15 degrees per hour, and then latitude, you know that it's going to be associated with 24 degrees per year. I don't know how you'll associate longitude with 15 and latitude with 24, but that's a common, 1 out of 35 points right there. You're 3% on the way. Okay, using the data in this table, and let's see. Using the data in this table, under which conditions will a PV module produce the most amount of power? And we're going to go through all these questions. So if you have to cut out a class today, just come back in between 2 to 4 and retake the exam tomorrow. If you retake the exam tomorrow or later tonight and get it correct, I don't know if you're staying tuned, you could just go ahead and do it. You retake the exam tomorrow, get a passing grade, we'll get you your completion certificate. Otherwise, you're going to have to keep reviewing the answers and keep taking it until you pass. So under which conditions will a solar module produce the most amount of power? So everyone should have gotten this question correct. We got one measurement here it's 1,000 watts per meter squared or 800 watts per meter squared, and the 1,000 watts per meter squared is more energy than 800 watts per meter squared. So it's not going to be the 800 watt per meter squared answer. So then it becomes, okay, is it 1,000 watts per meter squared at high temperature? Or is it 1,000 watts per meter squared at cold temperature? Remember, we talked about this in class. If all else is being equal, the same amount of power on the surface of the module, 1,000 watts per meter squared on the surface of the module, and all else being equal, it's the cold temperature that produces the most amount of power. And so the right answer is this cold temperature, where you still have a lot of energy on the surface of the panel. That's under these different laboratory tests, the cold temperature with a high amount of energy will result in the most amount of power. So which document provides the open circuit voltage, short circuit current, maximum power, and dimensions of the solar panel? That's the module specification sheet. You know, the one-line diagram is a simplified three-line diagram. A three-line diagram is similar to the wiring diagram, and so all of this information, except the module dimensions, would probably be on a three-line or one-line diagram, but all of this info is definitely going to be on the module specification sheet. Probably won't be on the site plan. Which of the following is monitored by an automatic transfer switch? So an automatic transfer switch is like that automatic cutover for a generator. So when the power goes out, a generator kicks on, it isolates the home from the grid. Now, how does that happen? Well, you could have a manual switch, go outside and flick a big giant switch, or you could have an automatic switch. And the cost of the manual switch and the cost of the automatic switch are actually close together, especially when you go and calculate the cost of the cable and the cost of the actual install. Automatic transfer switches are cheaper. Sometimes, for other reasons, you need to have a manual switch too, if the utility really cares about the kind of switch, whether it's a knife switch or a breaker. They might require you to install a couple different switches. But how does an automatic transfer switch work? Well, it monitors the grid, and when it detects a grid failure, it cuts the power. And so it's not monitoring the secondary source. Whatever it's backing up, you know, it's powering, whether it's in emergency mode, you know, or not. It's monitoring the primary power source, and if there's a failure in the primary power source, it switches over. So the answer is the primary power source. I hated this question, but y'all did really good on it. It says, which of the following affects the choice of inverter? You know, the orientation of the array, the shading at site, the available solar resource. You know, I would say that the shading at the site and the available solar resource are almost the same thing, and the orientation of the array is pretty close to that as well. And I think that, you know, the shading on site would determine the choice of the inverter. You know, whether you use a string inverter or a microinverter, a string inverter, a DC optimizer, the shading at site, you know, enters into that. So I think that would be a valid selection. The correct answer, in the eyes of NABCEP, or in the eyes of the NABCEP PV Associate exam, is out of all of these items on the list, the inverter's output rating is going to change depending on what inverter you use. So I guess they're saying the shading of the site, the availability of the sun, and the orientation of the array are all going to be what they are, but the power rating of the inverter would change based on what inverter you select. I think it's a poorly worded question, but y'all got it right by and large. They're not trying to, if all three answers are correct, then maybe the two that are if three of them are very similar to each other and they're all three correct, and there's all of the above answer, all of the above in this case would be wrong. The orientation of the array the choice of inverter doesn't really matter based on, I don't know. It's just a bad question. But they're saying, the inverter's continuous output rating is something that obviously changes based off what inverter you use, and that's more so than anything else on the list, and that's why it's the right answer. So, which presents the most significant type of structural load on roof mounted arrays? I hate this answer. I hate this question. I think it's a horrible question because, snow loads that sit on top of an array, they can be dead loads, like if they're just sitting on top of an array. Snow loads can also be live loads, as if the snow was on the array and then wind got underneath the rack and started picking all that weight up. That impacts the roof too. Wind loads are a live load, and so when I was taking this exam, I really thought that the answer was going to be live loads because they were going to look at all the combined effects of snow and wind and everything, and so I thought the answer was live loads. But the correct answer, I was overthinking it. Out of everything we've talked about in class in terms of loading, we mentioned that wind is around the edges of the array and around the edges of the rooftop. We didn't talk too much about snow load. If a solar array can go on the rooftop, it can go on the rooftop and manage the snow load, except in the most extreme environments. If you're in Buffalo, New York, and you're getting 5 feet of snow on your rooftop, that's going to be an extreme circumstance and a local circumstance, and it does have its own design hurdles to it. You have to put more attachment points on the rooftop to better distribute the weight. But on every solar array, you're going to reinforce kind of the corners of the array. The corners of the array, the edges of the array are going to have more attachment points than the interior of the array. Those concrete block diagrams we talked about in class on Friday, we saw how they want to weight down the sides of the array, but then they don't weight down the very edge of the array because they don't want the wind load to be really impacting that heavy corner of the array. And so there's a lot of design in the structure side that's based on wind. And the answer, in fact, is, NABCEP says the most significant type of structural load on a solar array is wind related. So one way to kind of remember that is just, what are you going to be most concerned about? The solar array in a blizzard, or the solar array in a tornado. In a blizzard, it might be covered up with snow. Okay. In a tornado, you want to make sure it hasn't been ripped off the rooftop. Wind is a little more dramatic in almost all circumstances. Which portion of the PV system plan set includes the locations of the major components on the property? So on Friday, we looked at a diagram that showed the array layouts and some proposed inverter locations and some points of interconnection. That high level view is the site plan. It's not the safety plan. The safety plan might show some disconnect locations or some eye washing stations or something, but the equipment data sheets, that's just going to show you the data of each particular equipment for the manufacturer. It's not going to show you anything site specific. The electrical diagram, see, that's tricky because on a simplified one-line diagram, you are indicating like the perimeter of the roof or when you're going into the building or outside the building versus the inside of the building. So there is some of site information provided on an electrical diagram, but they're saying, you know, the locations of the major components. A one-line diagram doesn't really tell you exact locations or even general locations. The site plan it'll tell you exactly where the thing should go. It just might not tell you the exact dimensions, but it'll actually locate where the things are or where they're proposed to be, even if it's not a construction manual. Which of the following is an approved method of structural attachment where trusses or rafters are not conveniently located on a sloped roof? I hate this question. I hate this question because this answer is almost correct. And it says, well, if you can't lag screw into the truss or the rafter, there are systems in the solar industry where you can go into the plywood sheathing. And in our engineering class, we actually go through, it's actually in the rooftop solar class in the second half of it. We go through some calculations to show that the decking of the rooftop is strong enough to support solar in many circumstances, not all. But you wouldn't use lag bolts to go into the sheathing. You would use wood screws. You would use something a little more appropriate for it. And you know, I think especially in years past, solar installers haven't had the balls to say, okay, you can actually go into the decking and not the rafter. You know, what NABCEP instead really wants you to think, you know, especially as a new hire or someone coming in, is that you have to go into the rafter, that you can't go into the sheathing. And that's not true, but there's a higher truth to that. And the higher truth is that a rafter is going to be so much stronger than just going into the decking, that if you can go into the rafter, you should. Okay, so you know, they're I think that secure the lag bolts into the sheathing, that's almost correct, except you wouldn't use a lag bolt. You know, adhere with roofing cement. There's been some experimental solar panels that have been just kind of stuck onto the rooftop, and so that has been a viable solution. It's not the solution NABCEP's looking for. Yeah, increase the span between attachment points. So you do get a span on your rail, and then your attachment point, this is a little L foot. You know, that's what gets the flashing that goes into the rooftop. You know, the span is the distance between, you know, L foot to L foot. And so often if your rafters are like 2 foot on center, you'll do a 4 foot span. But in reality, the rail can go in many times up to a 6 foot span, or even sometimes an 8 foot span. So there is flexibility in this span. In many cases, installers generally go with a conservative span. They say, you know what, we can go 6 or 8 feet, but if I go 4 foot on center, then, you know, I'm over engineering it and it's going to be just fine. So increasing the span between the attachment points could actually work, but you're still having to locate where the rafters are, and maybe you increase the span and get out of spec. So again, I think that this is actually a pretty good answer. It's not the answer that NABCEP's looking for. What NABCEP is looking for is a process called sistering rafters together. Sometimes it's called daughtering rafters together. So there's actually a sistering versus daughtering is whether or not you're taking an extra piece of wood and making that rafter a little bit thicker. So you take this rafter and you just put a block of wood right next to it so that you have twice as much space for that lag screw to go into. You know, maybe you get a crazy structural engineer who doesn't want you to lag screw in the rafter, but he'll say, you know, just put a piece of plywood right next to the rafter and screw into the rafter, but have your lag screw go into that extra piece of wood block. Sorry, not plywood, but wood block. And that's fine. Now, sometimes instead of putting the block of wood right alongside or right next to the rafter, you might put it between two rafters. You know, you might, you know, really kind of what I'm thinking about is these, if you have like a barn roof like this, and you're not really certain that you're going to be able to get right into the rafter because of the roof decking and these wood battens, and how do you guarantee that your lag screw is actually going into that rafter? You know, what you might do instead, and ignore the errors with this roof, but what you might do instead is put some wood blocking. You say, okay, well, I know I can identify where this purlin is or this batten is, and I know that I can hit that. And so I'm going to put, you know, some wood blocking, you know, all the way across the whole roof surface in order to, you know, have my lag screws eat into not just the dimension for this batten, but, you know, I might put some wood blocking in between these joists and just go into that wood blocking. So what NABCEP is trying to say in this question is that it is acceptable to put wood blocks between the rafters and the trusses to give you more surface area to lag screw onto. And what is really bad about this question is all the other solutions have a time and a place in the industry, but they're saying, you know, what is the standard? Not thinking creatively. You know, if you have lag screws that need to go into a rafter and they're not able to be located right on the rafter for whatever reason, you know, adding some wood blocking into that attic space is a viable solution. You know, whether or not that's a great question, hey, yeah, I don't think so. But I'm not making the questions on NABCEP, and I'm not making the questions on this practice exam. This is, you know, you gotta be ready. Now, which type of inverter is best suited for applications with multiple roof angles and orientations? Most of the class got this right. It's microinverters. A string inverter is like a whole bunch of panels on one circuit. DC optimizers or microinverters have little boxes behind every panel on the roof, and those little boxes allow individual panels to operate independently from each other. So often you're going to get questions about panels at different orientations. In fact, we already saw one earlier about the choice of the inverter, and it said, and it was something else that wasn't about the orientation of the array. But you just have to focus on the exact question. This question says, in inverter selection with multiple roof angles and orientations, what are you going to want to use? And they're giving us a standalone inverter and then a string inverter, and then a bimodal inverter versus one inverter per every solar panel on the roof. And the giveaway here is if they had called it micro inverters instead of micro inverter. So they're being a little tricky, but the answer is micro inverters. A bimodal inverter would be a battery inverter. A grid-tied string inverter is a standard one inverter for the whole system. A standalone inverter could be a battery inverter, an off-grid inverter. Maybe it's a grid-tied string inverter. All right, so what is the purpose of the rapid shutdown system on roof-mounted objects? The purpose is to ensure the safety of the firefighters and the emergency workers. So one answer was it provides a convenient disconnect switch at the array. It does that. I think this is a terrible question, but maybe the NABCEP PV Associate exam is full of terrible basic questions that you're going to have to just boil down to, what is the most important thing going on here? And I actually asked you a question in class about safety glasses, about do you wear them because it's an OSHA requirement, or do you wear them because they protect you from poking your eye out? The important thing is you wear them because it protects you from poking your eye out. But in an OSHA exam, the answer might be it's an OSHA requirement. NABCEP, on a question like this, what's the purpose of the rapid shutdown system? We have one answer. It provides a convenient inverter disconnect switch at the array. Well, the disconnect switch is really, it's on the ground. It's not up on the roof. In Australia, they have disconnect switch requirements where you have to go up on the roof. But this rapid shutdown switch is for a fireman to come up and on the side of the building, press a button to de-energize the whole system. So they're being sneaky because a rapid shutdown switch is a convenient switch that disconnects the system at the array that is between the solar array and the inverter. So it is an inverter disconnect switch, but that's not the right answer. Very close. That's what it is. Maybe it's not the purpose of what it is. It limits the current and voltage outside of a given array boundary. I think that that's a valid answer too. Rapid shutdown limits the electricity of the solar array to the solar array itself, but it's gotten stricter and stricter as time has gone on. It used to only limit outside of the array perimeter. Now it also governs inside the array perimeter as well. These are both very similar answers. It provides access to series string fuses. By shutting down the system, it does provide some access to the series strings fuses. It's not a perfect answer. There's other considerations, but the point is, on this exam, on the NABCEP PV Associate exam, if there's a question about the purpose of the safety system, the answer is going to be firefighter safety. What I would do with these questions is to say, which terms have I not heard of before? If I see the question and it says rapid shutdown system, I have no clue what rapid shutdown is. Ask the question in the Discord, we'll get you an answer. Which criterion is used to determine the maximum fuse size allowed of a PV source circuit? I hate this question. If I'm an electrician and I'm doing fuse sizing, I'm looking at the ampacity of the device and then applying my National Electric Code driven safety parameters. And so, every single time I'm sizing a fuse, I'm looking at the ampacity rating of the PV output circuit conductor, or because that's the PV circuit, or I'm looking at the ampacity of the inverter output rating and applying oversizing protections and setting my fuse size. Kind of a weird answer. The PV module manufacturer series fuse rating. I think that this question is borderline wrong, borderline confusing. But what it's saying is, if the manufacturer is telling you to use a specific size fuse, then use that specific size fuse. If you open up the manufacturer manual and it says use a 15 amp fuse, then use a 15 amp fuse. So in this case, they're saying maybe there's some sizing issues that your electrical calculations haven't considered. That's baloney, by the way, but they're saying if the manufacturer is telling you to use a specific fuse size, use that specific fuse size. Which of the following best describes the function of a DC to DC converter or a DC optimizer? We didn't go over this in class. We didn't go over how a DC optimizer works. So you're blindly guessing on this one, and we got a pretty even distribution. And to answer this, you really have to know series wiring versus parallel wiring. And in series wiring, along one circuit of solar panels that are wired positive to negative, positive, negative, positive, negative, voltage is adding up and amperage remains the same. So that diameter of cable that connects all the panels together is the same thickness, and that current that's flowing through it is the same thickness. Its voltage is adding up. When you get two circuits or more, and the bottom one is circuit 1 and the top one is circuit 2, and it comes time to wire these circuits together, and so you connect all the negatives together and you connect all the positives together, or in your electric service panel, you connect everything to the same power feed in the breaker panel, and then you connect all the other ends to the neutral, to the drain on the other end. When you're connecting all the circuits together at a common point like that, that's parallel wiring, and in that case, amperage adds up and voltage remains the same. And so DC to DC optimizers are different than microinverters, and I don't know. The DC to DC optimizers are run positive to negative, positive, negative, positive, negative. And so the way that the DC optimizer systems work is by basically by fixing the output voltage of the circuit itself and judging and varying the amperage. So how do we do this? It says it maintains the rated voltage of the individual modules while adjusting the current. Yes, that is what it does. I would say that is a right answer. It adjusts the voltage of the individual modules to maintain a fixed current. Well, a volt times an amp is a watt. And so for the same amount of power, if adjustments are being made to the voltage, then the amperage is going to change. So this is not the correct answer. It maintains the rated output current under shading conditions, or individual strings under shading conditions. Well, that's a tricky question, because optimizers do that. They account for shading conditions, but they don't do it by maintaining the output current. And so here's an answer where they are maintaining the output, maintaining the current, adjusting the current. I think that this answer is correct too, and I would challenge NABCEP if you got that wrong, because these optimizers work by fixing the output voltage of the circuit, but adjusting. I guess that's why this one's wrong, is because it adjusts the voltage and it adjusts the current. And here it's saying it's maintaining the voltage of the individual modules. It's a poorly worded answer. But what this answer is saying is optimizers work by maintaining a fixed circuit voltage. So along this circuit, the individual panels are being adjusted, but the output voltage is the same. And so I don't know, maybe you're gonna have to just remember this one, because it's likely to show up on the NABCEP exam, because it's talking about the function of DC optimizers, and they work by making tiny inline adjustments, and they're being wired positive to negative, positive, negative, positive, negative, to keep the voltage fixed on the output of the string. I guess I'm trying to struggle on how to best explain this, but the DC optimizers are wired in series, and in series wiring, it's the voltage that's going to jump up and down, and the optimizers fix that. And because they fix the voltage, now it's the amperage that's going to jump up and down, but it's not the actual individual panel modules that are maintained, it's the circuit voltage. Normally, all the modules would have to be jumping up and down at the same voltages, and the I don't know. Strike out on explaining that one. It's the function of the system. You're not gonna understand this until we talk about it in our residential off-grid class at the end. We get into optimizer spec sheets. So if you want to know more on that, I can steer you towards it. But optimizers fix the voltage of the circuit regardless of the individual module performance. That is the most accurate statement about how they work. So that's a memorization one. Okay, what is the minimum working clearances around the inverter? So we got 80-inch height, 80-inch height, 36-inch height, 30-inch height. So it's probably going to be one of these two. Well, the question is it 36 inches in front and 30 inches side to side? Or is it 30 inches in front and 36 inches side to side? And the way I remember this is there's more, the side to side is 30 inches. It's only enough space for someone to stand in front of a piece of electrical equipment that they're working on and be able to work on it comfortably. So is it going to be more comfortable if you have, 3 feet from right to left versus 2.5 feet from right to left? A human is about, maybe 2 feet wide, maybe 2.5 feet wide. But if you're working, in a inside a cramped coat closet and all the coats and junk and stuff are like right behind and in front and around you, that distance to be able to stand in front of the panel and actually work the panel is important. So if it's a question between having 36 inches from the front of stick your arms out straight, your arms are out straight. I hope that those arms and those fingers are sticking out further than what you are wide. I hope we're not all like 500-pound circles where, we're as wide as we can reach out in front of us, but your shoulder width from shoulder to shoulder should be skinnier than that distance from when you stick your hands out in front of you. So if the question is it's better to have more shoulder to shoulder width and less distance to work comfortably in front of you, or the other way around, the code is going to go with the safer of the two. It's better just to work in your little lane, in your narrow lane, but have enough space to work up in front of you instead of you being shoved into that electric service panel. So in fact, electric code, it's not just 3 feet behind you or working area. It might actually be more than that depending on what's behind you. If there's a wall, if there's open space, or if there's electrical stuff behind you, this number actually can increase in distance. But most of y'all got that correctly. It's about it's a little over 6 feet tall, 6.5 feet tall, 30 inches wide, 36 inches of depth to work in. We have a National Electric Code class, and it's a really good introduction to National Electric Code. So it's a daunting task, but there is a National Electric Code class in the classroom if you want to review it. And I realize we're getting to the top of the hour now. You don't have to stick around. I need to finish this recording. So I'm going to finish the recording and then send out an email. But basically, you just need to, once you take this test again, same link, just take it twice. Once you take the test again and you pass it, I'll give you your completion certificate for the program. What is a standalone PV system considered under the NEC labeling requirements? So this is as unclear of a question as you can possibly get. A standalone PV system. Still don't know if they're saying that's a battery system, an off-grid system, or a grid interactive system. So I don't, it could be it could have a battery and be off-grid or be grid connected. I don't know what they're saying by standalone. In other questions, they've used utility interactive. So I think they're saying a standalone system is a off-grid system with a battery, but I'm not sure about that. Now, the correct answer is power source. So is it an energy generator? Is it a storage system? Is it an interactive system? Or is it a power source? Well, we do know that it is going to be considered it is a power source regardless. So everyone who went with power source played it safe and got the answer correct. I actually, when I took this exam, I guessed storage system, but that's really not a National Electric Code term, nor would be a energy generator. A generator would be a battery would be, code considers it to be a power source. All right. Interactive system would also be a power source, but that's the answer. what is the purpose of a visual inspection? The visual inspection is to identify easy to find problems without using instrumentation. So, that inspector on site, when it comes time for him to inspect, he's not really there to prevent you from burning the house down. He's there to put his experienced eyes on your project to see if there's something wrong that's apparent to him without getting too far into the details. He can tell how good of a job the installer did visually. If you can tell how good you did visually, that could indicate larger problems or not. I did an inspection a couple of weeks ago where a cable did not appear to me to be as thick as it needed to be, and right off the bat that led to a huge kerfuffle, because if the system had been turned on, it could have easily burnt the system down, the home down, and that was visually apparent. So they're telling the key here is a visual inspection rather than a electrical inspection. Like, you might be using a voltmeter or a multimeter to investigate faults or faults. The visual inspection is to find easy to find deficiencies. Like, a common visual inspection is looking underneath the solar array for bad cable management to see if the cables touch the roof surface or not. So which tools are used to identify loose electrical connections that create heat? A multimeter is probably what I would be using, but then I would still be guessing where that loose connection is until I de-energized everything and checked all the connections. That multimeter will tell you there's a problem going on, but it won't necessarily tell you where it's at. An irradiance meter is a good choice, but an irradiance meter measures the amount of sunlight in the air, not thermal scanning. So the only thermal temperature scanning answer here is this infrared non-contact thermometer. I actually think when I took the NAPCEP exam years ago that I selected a radiance meter, because I was like, oh, that measures sunlight or whatever, or it measures the amount of energy in the air, so that has to be it. It's the thermal red, the infrared scanner is scanning coronavirus whenever it's coming in the door by pointing at you and taking your temperature. That can be used to a thermal scanner is useful in the inspections. Loose connections will generate heat, that'll show up accordingly. What is the power rating of the solar array that consists of 30 265 watts and 3 series strings of 10 modules each? So there's 30 solar panels. There's 265 watts. The power rating is 30 panels by 265 watts. So it's not going to be in watt hours. They don't know how long the solar array is going to be on or not. And there's 30 of them. So they're talking about the power rating of the total solar array, not the power rating of an individual circuit. 10 modules, 265 watt modules. Each circuit will be 265 kilowatts, but it's the 7.95 kilowatts is the power rating of the system. So 30 times 265, the power rating of the whole solar array, 30 times 265 watts. Almost done here. For which environmental factor can the DC current of the array be calculated using the module's nameplate current? So, if we know what the module, what is this saying? You know, the using the module nameplate current. That the nameplate current is what's on the spec sheet. So the module says it should be producing this much current on the spec sheet. And then it's saying, well, based on what other environmental factors can we calculate the actual current? What will the actual current be? So we've talked about in class how voltage and current can be impacted by temperature. And so temperature is definitely on the list. So we can take out the other stuff, you know, that doesn't involve temperature. We know temperature is definitely on the list. So the other question is, well, was the irradiance, that's the amount of sunlight in the air. Does the amount of sunlight in the air matter for current? And the answer is yes. On the module spec sheet, there's irradiance charts that show for different temperatures and different amounts of sunlight what the voltage and current is. So the correct answer is irradiance and temperature. You know, wind speed it does not impact solar performance that much. If you go into a PV watts calculation for a roof mount versus a ground mount, you know, they say the difference in wind speed for that air being underneath the solar array has an impact, but it's like less than 1%. It's not that important. So it's not something where you could really, because the wind is blowing this fast, you know how much power the solar array is producing. But we know solar is going to be impacted by temperature. We also know solar is going to be impacted by the amount of sunlight in the air. That's how they got to that answer. So which PV system component provides performance analysis information? There's monitoring systems within the inverters. So that's where we get our solar monitoring from. The irradiance meters are used to analyze solar performance. So if you don't know if your array is producing correctly, having a gauge that tells you how much sunlight's in the air can be useful for diagnostics, but that's not what it's asking. The utility meter will tell you if the solar array is on or off based on if the meter is, you know, giving you any credit for solar production. But that's not enough. You know, it's just, you know, the correct answer is inverter. Which component provides performance analysis information? You know, all of these things might provide some information, but the inverter has a monitoring system. It's what we're wiring with Ethernet, is the inverter monitoring. The inverter's the lifeblood of the system. It's the brains of the system. It's the heart of the system. You know, it's complicated and it has electronic monitoring in it. Did pretty good on this question. I don't like the term soiling. You know, what that really means is dust. And this question is, what's the most common maintenance issue in dry climates? And so the question is, why are they telling you dry climates? Not, you know, what is normal or to be expected. Like, I think a common maintenance issue, no matter where you are, is loose connections. And a lot of people answered that. You know, that's a good guess. If there's something wrong with electrical work, it's commonly loose connections. It's often loose connections more than it's dust in terms of the most common maintenance issue. Um, so I don't, maybe most is a bad word here. Maybe it really should say what is a common maintenance issue in areas of dry climates. But maybe the guy who wrote the question thought, well, if I say which maintenance issue is more likely in dry climates than not dry climates, maybe that'll make the question too easy. Uh, Whatever. It's kind of unclear. It might not be true. You might have loose connections in dry climate solar array more often than any other issue. But the thing is, why are they asking about dry climates? And the answer is dust. If you have a solar array along a dirt road and there's cars driving up and down that dirt road and it's kicking dust into the air, that solar array is going to have more dust on it than if it's not in that dusty environment. And so, even if you disagree with this question, even if your own field experience in solar, you know that loose connections are the main problem of solar. This for the quiz, you're saying in a dry climate, that dry climate term should be what's keying in on soiling being the answer. The NABCEP exam can be a little behind the times. But it's asking about dry climates. None of the other things have as much to do with dry climates as dust. So that's why dust is the answer. I didn't know the answer to this one. What is the OSHA regulated maximum distance to the eye washing station? I think it is much more likely that you're going to get a question about how many feet should the ladder stick up above the rooftop. And we learned that in most cases that's 3 feet. Or you're going to have a question of when do you need to wear a hard hat? And we talked about the answer to that. You don't need a hard hat on a roof. You need a hard hat down below. You need a hard hat where things can fall on your head, where you can hit your head. There's construction equipment around. You need a hard hat. The distance to the eye washing station is 25 feet. And then I thought this was a terrible question. Which publication addresses safe work practices to help protect personnel from workplace injuries and fatalities? I put fire code because I thought that this would be covered in pretty much all of it. But here's the thing. National Electric Code is not covering workplace injuries or fatalities. It's covering good electrical design. Fire protection and life safety systems is only a specific kind of safety equipment. Fire code is like the table of contents for everything else. And so the answer is the standard for electrical safety in the workplace. This is not National Electric Code, which is NFPA 70. This is NFPA 70E. That's one of those things where it might be a memorization question that you just brush up on before going into class. Oh, if I see this NFPA question, the answer is going to be probably NFPA 70E. It's not National Electric Code. It's the thing that's more safety related. So that's the exam. So it can be frustrating. I imagine if you take the exam over again, now that you know the answers, you should do a lot better. And so what I want you to do is actually, when you're done watching this video, actually go in and take the exam over again. We took it at the beginning of this class, and then just go through it now and take it again. First off, you need to do that. You need to pass this exam in order to get your class completion certificate. But second, it'll just better solidify some of the stuff we've talked about in class. And if you fail it the second time, then it'll also tell me that I need to give you some additional kind of viewing assignments to shore up some of the concepts in class. But go ahead and take it, and when you're done, just wait a few days. We'll get you your completion certificate. If tomorrow we're doing office hours here just like today, probably for 2 hours instead of three and a half. So I'll be reaching out to you. There's a couple of students who need to make up some makeup days. I'm not quite ready for that yet, so hang tight or just work with me individually. But the last thing we need to do in class to close out here is you need to pass this exam. So, keep taking it till you pass it. If you're really struggling, we might have to do a few more hours of general knowledge building. Don't be intimidated by the exam. The PV Associate exam, every time you take it, it costs $125, which is not money you want to lose, but it's not the worst thing in the world. In fact, I think it's the review tomorrow is going to be very similar to this review today. It's not going to be anything new unless something jumps out at me from the exam that we have to cover. But really what we're trying to do now is get y'all closed out of class. So we're trying to get you to pass this exam, this practice exam, and then get you your completion certificate. That doesn't mean you can't come back into the Discord group and use it as a resource. In fact, when it comes time for you to actually take the solar exam, we want you back in here doing some reviews and letting us know you're about to take it, so that we might do another different kind of exam prep for you. So I guess what I'm trying to say is, if you go ahead and pass the exam, then you don't need to come back tomorrow. But if you want to, the more the merrier. But I guess what I was saying is, if you go and you take the NAVCEP exam and you fail it, the only thing that happens is you have to pay the $125 exam fee over again. Maybe you have to pay it on your own if someone else paid the fee the first time. But the strategy of just signing up for the exam and trying to pass it, and then remembering all the questions that you had struggled with right when you're done with the exam. Like if you take the exam and you feel like you did pretty bad, don't just get overwhelmed and leave. Take that time to look at the exam questions you don't know the answers to. And if you can remember the terms or concepts that you're struggling with for even 5 or 6 of those questions, just take the rest of your time in the exam remembering what the questions are, and then write them down as soon as you leave the room, and come back into here and ask. And then a month later you can take the exam again, and it might just be that if you had gotten 5 or 6 more questions correct, you would have passed. So failing the exam is not the worst thing that can happen. In fact, if you were trying to do this in the quickest amount of time, it might be just going ahead and taking the exam and failing, and then taking it again a month later could be a viable strategy. I don't know. I usually pass on the first time, but I know a lot of solar installers who didn't pass on the first time, and I think just taking the practice exams right the day before is the best way to do it. Okay, so we are out of time for this program. About 20 minutes over. I'm gonna go ahead and end the live stream, but I'll stick around for questions if y'all have any. Otherwise, I'm going to be looking at these responses. If you've done well on the quiz, I'll get you your completion certificate. If you're like at a 65% or less and you've taken the quiz twice, then I will probably send you some videos to watch or review some of that stuff tomorrow and then send you that video to watch. So, with that, y'all have a good evening. Um, See you tomorrow. If I don't see you tomorrow, we're getting our NABCEP application together for Edison. It'll take NABCEP a couple of weeks to review it, and as soon as they approve it, you'll be able to take the exam. So maybe in 3 weeks from now, y'all will be ready to schedule the exam, and at that time come back, let me know, and we'll get a different NABCEP review with different questions, same topics being covered, but um, that'll get you real well prepared. So I think if you're nervous about the exam, if you don't think you're going to pass the exam, if you took this and you're like, oh screw it, these questions are horrible, I'm not going to pass. Don't worry about that. It's like the day before the exam, come back here, take this over again. If we haven't, we'll probably have another practice exam for you by then, and and taking 2 practice exams the day before the test will help you get a couple of questions correct and just improve your odds a little bit more. Yeah, so after you pass the practice exam, um, we still got to get Edison set up. These NABCEP classes generally cost a ton of money. Like just the training program, $1,000 or more. Edison and Solar Landscape and I have all kind of come in together to deliver this at a lower price. So I think that Solar Landscape is going to work with Edison to get y'all taking the NABCEP exam. And certainly some of you have been crushing it on the quizzes, will absolutely get put into it one way or another. As far as everyone taking it, I think that's in the work too. I'm not Solar Landscape, so I'm not certain about it. I'm not Edison, so I'm not certain about it. But I know that's what everyone's kind of intent is. But I have to get Edison's application set up, because if we ran y'all through my existing NABCEP accredited partner, the added cost would gobble up a whole bunch of extra budget. So we're going to get Edison set up, and that makes it a little bit cheaper. I think the goal is to get you into the NABCEP PV Associate exam and get you to take it. I think the costs are going to be covered for at least the first time around, but you can't hold me to that because I don't really know. But in short, yeah, in a couple of weeks' time, Edison will be able to schedule you for the NABCEP PV Associate exam, and I think, especially in this first group of students, I think the intent is to get all of y'all tested for it, and hopefully more than half of y'all will pass it. I think that most of you should be able to pass it if you come back and use the classroom within a day or two ahead. Okay, so I'm going to disconnect the live stream and I'm going to